if you are only trying to learn coding and running away from the hardware, this video is for you.
Go, in and out, 20 minutes adventure.
Have you ever wondered what actually makes robot move? You might be thinking it is artificial intelligence, or maybe it is computer vision, or maybe it is ROS. But before a robot can run application, detect object, or make intelligent decision, there is something much more closer to the hardware that make all possible. And there is what embedded engineering comes into robotics. In this video, I'm going to explain what embedded engineer does and how embedded system work inside a robot. You actually need to learn. How embedded engineering connect with robotics. If you are someone who want to become a roboticist, understanding embedded system can give you a completely different perspective on how robot really work. So if you are only trying to learn coding and running away from the hardware, this video is for you. Okay, let's start with the physics question. What exactly is embedded system? An embedded system is basically a computer designed to perform a specific function inside a larger system. Your laptop is a general purpose computer, and you can browse the internet, edit a video, run simulation, write code, do thousands of other stuff. But embedded computer is usually designed for much more specific job. For example, a motor controller, or a flight controller, or a sensor probe. A robot controller, a washing machine controller, the car electronic control unit, all of these can contain embedded system. The important thing is that the embedded system are actually working very close to the physical world. They read the sensor, they control motor, they communicate with other hardware, and they react events. And how they have to do, all of this reliably. That is exactly why embedded engineering is so important in robotics. So what is the difference between an embedded engineer and a software engineer? The biggest difference is the relationship with hardware. The traditional software engineer might write application that runs on Linux, Windows, or Android, or Mac, or the cloud. The embedded engineer might write software that runs directly on controller. For example, imagine we have the robot wheel. The high level software might say move forward 1 meter per second, but the model doesn't understand the command directly. Something has to translate that high level command into the electrical signal. The embedded system might control PWM signal and re-encode the feedback, calculate the motor speed, and communicate with main computer. So you can think about robotics as several layers. At the top, you have something like AI, planning, computer vision, ROS navigation. Then underneath that, we have low-level control. Then underneath that, we have actual hardware. Embedded engineering leads very close to the lower level. Let's take a mobile robot as an example. Imagine I tell my robot to go forward, and that sounds simple. But what actually happens? The navigation system calculates the velocity and processes velocity command. The motor controller receives the command. The controller calculates the required motor output. The microcontroller generates the PWM signals and the motor spins. The encoder measures the motor movement, and the encoder data comes back to the controller. The controller compares the desired speed with the actual speed, adjusts the motor speed. This happens continuously and very quickly, and this is where embedded engineering became extremely important. Because if your embedded system is badly designed, then it doesn't matter how good your AI algorithm is, your robot can still behave badly, and it might be oscillate, it might move inconsistently, and it might misencode the paths, and it might overheat the model, or it might lose the communication, or it might simply crash. A robot is not just a software. A robot is a combination of software, electronics, mechanisms, and control. The embedded system sits right in the middle of those worlds. So, what does an embedded engineer actually do every day? There are many different areas. One of the most common is microcontroller programming. You might work with microcontrollers such as STM32, ESP32, Arduino class board, or other industry MCUs. You write the firmware that interacts with hardware. For example, reading the encoder, reading the IMU, or controlling the motor, reading the temperature sensor, and controlling LEDs, communicating with other devices. By the way, another major part is communication protocols. You will often encounter things like UART, I2C, SPI, CANs, USB, Ethernet, and sometimes more specialized protocols. For robotics, CAN is particularly interesting because it is commonly used for communication between controller and device. For example, you might have a main computer communicating with several motor controller or over CAN. Then there is debugging. And honestly, debugging embedded system can be very different from debugging normal software. Sometimes your code looks completely correct, but motor doesn't move. So you start checking if power supply is working, or if voltage is correct, if this communication is working, or if GPIO configuration is right, if the PWM frequency is correct, and if encoder is connected, is firmware actually running. This is why embedded engineers need to understand both software and hardware. Now let's talk about programming. The most important language for embedded engineering is C. C gives you the very direct control over memory and hardware. You will often see C. C is for microcontroller firmware. Then there is C++ or C++. C++ is extremely important in robotics because many robotics framework and performance critical software use it. For example, Pros2 suppose both C++ and Python, but C++ is especially useful when you are working closer to hardware or need high performance. And then there is Python. Python is incredibly useful for robotic AI testing, automation, and toolings. So personally, I would think about this as should I learn C or C++ or Python? I did think now all three, but understand where each one fits. C is extremely useful for the low-level embedded system, and C++ is powerful for robotics and performance critical software, and Python is great for higher level robotics, automation, AI, and experimentation. One concept that became very important when you enter embedded engineering is real-time system. Real-time doesn't necessarily mean very fast. It means that the system has responded within predictable amounts of time. It means imagine you are controlling a motor. You want to update your controller every 1 millisecond. If your system update after 1 millisecond, sometime, but after 20 milliseconds, other time, your controller can behave unpredictably. This is why embedded engineers care about things like interrupt, timer, and scheduling, and latency and jitter, deterministic behavior, and real-time operating system. I'm gonna make a video about RTOS later, real-time operating system, free RTOS later. You usually encounter RTOS such as free RTOS, where you can create different tasks for different jobs. For example, one does read sensor, and another control the motor, another handle the communication, and another monitor system health. And this is very different from simple writing a Python script on your computer. You have to think about timing, you have to think about resource, and you have to think about what happens if something fails. Now, let's connect this to something many roboticists know. ROS2 usually run a more powerful computer. For example, a robot might have and NVIDIA GSM. I don't have the NVIDIA GSM. So or Intel computers or the Raspberry Pi, another Linux-based computer. You can use other system too, but I don't recommend that. The computer can run ROS2, navigation, SLAM, computer vision, and AI model planning like motion planning or path planning, and many other applications. But you probably don't want your main computer directly handles or handling every low-level hardware task. Instead, you can have microcontroller need the low-level control. For example, to say I want the robot to move at this velocity, and the embedded system, the embedded controller receives this command. It controls the motor and it re-encoder, and then it sends the feedback to ROS2. This creates a very useful architecture. High-level computer and low-level embedded controller. The high-level computer think about what the robot should do, and the embedded controller focus on making hardware actually do it. And this separation can make your robot much more reliable and easier to develop. Now, here is the interesting part. If you want to become a robotics engineer, do you need to become a full-time embedded engineer? Not necessarily, but I strongly recommend understanding the fundamental. At minimum, you should understand microcontroller, GPIO, PWM, and ADCs, timer, interpret, you add I2C, SPI, CAN, encoder, motor driver, and business electronics, and C++, and basic control system. You have to become an expert in every single topic, but you should be comfortable enough to look at a robot and understand what's happening. For example, if your robot isn't moved correctly, you should be able to ask, is that a mechanical problem, or an electrical problem, or motor driver problem, or encoder problem, the firmware problem, and communication problem, or ROS problem, or navigation problem. Think it and suffer it. But there is valuable skill. Because robotics is not about knowing only one field. It is about understanding how multiple fields interact with each other. So if you are starting from zero, here is the simple part I would recommend. First, learn physics electronics and understand voltage and current, resistance, and motor, sensor, and circuits. Then learn C programming. Don't just learn sentence. Try to understand memory, pointer, structure, array, and how programs interact with hardware. And then get a microcontroller, STM32 or ESP32. Another development board is enough to start. Build a small project and read a sensor and control LED and generate PWM, program motor, encoder, communicating with UART, and then try I2C and SPI. Then learn CAN. After that, learn about real-time operating system concept, RTOS concept. And once you are comfortable with embedded system, connect with your microcontroller to a Linux computer. You can use Windows or Mac, but I don't recommend that. Then start connecting it with ROS2. And at the point, you are no longer just programming a board. You are building a robotic system. So, do you actually need embedded engineering to begin robotics? My answer is, you don't have to specialize in it, but you should understand it. If you are main interest in AI or computer vision, you can focus heavily on those areas. If you are interested in robot control, autonomous vehicle, and drone, robotic, or mobile robot, embedded knowledge become even more valuable. Because eventually, You have to connect your algorithm with physical world. Your algorithm doesn't exist in isolation anymore. It has to control the real motor, a real sensor on the real robot, and the real hardware. And the real hardware doesn't always behave like your simulation. And there is probably the most important things I want to take away from this video. Robotics isn't just AI. It isn't just robots. It isn't just electronics. It isn't just mechanical engineering. Robotics is a combination of all of them. Embedded engineering gives you the ability to understand what is happening underneath your robotics software. When you understand both high-level and low-level side, you can build better robots. You can debug faster, and you can communicate better with other engineers. And most importantly, you can understand entire system instead of only one part of it. If you are learning robotics right now, don't be afraid to go down to the hardware level. Learn C programming, learn microcontroller, connect with sensor, and control a motor, read the encoder, break something, and debug it and do it again. Because there is how you start becoming not just someone who uses robotics software, but someone who can actually build robots. That's for today. I'm tired. See you later, guys.
I can't fucking do this anymore! That was seriously fucked up. We almost died.